introduce you to the students. Good evening, students. Today is our first series of the guest lecturer. Our first guest lecturer is Dr. Arosha Senanayake, if I'm correct. Okay.
That's fine. That's fine.
Dr. Arosha is a senior member of IEEE, is the founder and leader of IntelliHealth Solution technology license, and he gained a well-balanced portfolio on research, education, especially teaching and service. Currently, he joined the University of Malaysia, UMCH, technology in Brunei Darussalam is establishing a joint venture with Asia Pacific region, ASEAN, a joint venture within APEC region. Dr. Arosha joined Monash University as a senior lecturer in mechatronics engineering in 2002, and also a senior in digital system. Today, he will teach asynchronous sequential circuit. This is the concept of for the students. This is the new concept because we already finished the combinational circuit. This is the first time they accept the sequential introduction, the introduction of sequential. Please.
That's right. That's great, of course. So that means really they haven't done anything pertaining to synchronous sequential circuits.
Yes, in the lab they already apply a counter,
Okay.
a design counter using FPGAs, using VHDL.
Okay.
But the concept, I haven't teach them the whole concept.
Okay.
So this is officially, this is the first introduction of the students using for sequencing.
Yeah. Thanks for the introduction. Thank you. Okay. Let me start then.
Please.
Yeah. Okay. Thanks for joining my lecture. Okay. Today we are going to learn about asynchronous sequential circuits. Having learned combinational circuits, you will come to know that no sequential circuits will survive without combinational circuits. Actually, all sequential circuits are controlled by combinational circuits. So then, therefore, anybody wants to really know about any type of sequential circuits, the fundamental is that first you should know combinational circuits very well. So then by now, I believe you all know combinational circuits. And then we are going to use those actually in this slide set. Okay, the idea is, of course, really learning objective. Yes, the expectation is to learn basic concepts behind really asynchronous sequential circuits, and then how we can really develop later on simple asynchronous sequential circuits in the laboratory session. So then I'm trying to go through little slowly because this is the first one. So then therefore, of course, you should understand what are the topics we are going to cover in today's class. In general, we try to understand what is the meaning of asynchronous sequential circuits, and then how to design asynchronous sequential circuits. Similar to combinational circuits, if you would have already designed like simple circuits like traffic light and so forth. I have seen really in your lecture notes. So then, yes, you can see that, yes, asynchronous sequential circuits is something little different to that. And then probably you would have followed some steps. And then here also you have to follow some steps. But at the same time, you should understand very well, yes, what are the critical conditions that may cause really asynchronous sequential circuits do not work compared to any other circuits, such as combinational circuits you learned, and then sequential circuits you are going to learn. Actually, asynchronous sequential circuits are quite critical in that sense. Let's see why. Yes. When it comes to sequential circuits, yes, we can define sequential circuits. If you look at really, if you can remember really about combinational circuits, what you had really some discrete inputs, and then we try to really obtain some outputs based on the logic gates really you really design, and then so you are planning to design some kind of circuits based on that. But of course, in case of sequential circuits, the word says sequential. Sequential circuits means actually uh, outputs thoroughly depends on not just solely inputs like combinational circuits. Uh, there are internal states. So what is the meaning of these internal states? We should know. You will know in short while. So then, in addition to inputs and outputs, you have some internal states. From where these internal states are coming? And so then there are two different types of sequential circuits: synchronous and asynchronous. Of course, synchronous circuits are quite easy because all circuits are really synchronized using clock pulses. So therefore, that is why it calls as synchronous. So then that means really output of each of the sequential circuit is subject to the clock pulse received by that particular entity, circuit or unit. So that really is based upon that out. But asynchronous, of course, there is no such clock involved, and therefore, of course, really output is not subject to really synchronically receiving clock pulse. But of course, sometime you might have two different clocks used really in two different circuits. So then really still you can make it asynchronous circuit. So we will see. So therefore, of course, what is going to happen that yes, the state changes, internal state changes occurs when one of the input variable is changed. Of course, if we have really more than one variable, all variables can change, but then that might cause many issues, particularly that might lead to really hazardous conditions, as we are going to learn in the coming slides. So then you can see that the basic difference is that, yes, other than inputs and outputs like in combinational circuits, what we have here, internal states. How these internal states we are getting? Oh, importantly, what we have is, as you can see from this slide, so there is a feedback from the output of combinational circuit to the input of the combination. So then therefore, of course, really what is going to happen that output is not solely depends on the inputs really you have from combinational circuit design, but at the same time it is also governed by the so-called feedback. This feedback is coming straight away from the output, as you can see. So then usually what we call that one as really intermediate outputs. So that is why that's not really exactly the output we desire to obtain. Outputs you can see on top, really one straight line, but in intermediate outputs produced really as will go through kind of a storage element, and then sometime this storage we can call as memory element. But of course, we don't really require memory as such, because we might use really some time really probably a simple logic gate as a time delay element, so that really yes, there will be delay to really get into the input of the combination. This is very stubborn when it comes to the outputs produced in subsequent intervals, subsequent times frames, because the thing is that actually combinational circuitry produces a kind of a intermediate output, so-called next state, and next state that it goes through the storage element and then get as the to the combination circuit as really a so-called really additional input to the combination circuit. So therefore, of course, we have to understand clearly. So the idea behind this, but this is really important when it comes to really circuit design. So combinational circuit really, as I have mentioned previously, yes, it is kind of discrete elements. So then you know very well that discrete elements in this case means zeros and ones. So that's all. But of course, really, whether we can have really some storage, some memory capabilities in combination, say, oh, absolutely not. So that's where really this feedback is important for us to retain some of the values, and those some of the really values so that really provides kind of insight into the variations of the input variables and that transform into the output. So that's how really asynchronous circuits work. So in this case, we don't need really a clock. So then if you would have really studied about flip-flops, of course, really you can use unclocked flip-flops. So then as the memory element, and then mostly what is happening really in the storage element, that's the key point really. Mostly in the storage element happens is that, yes, the value, next state value, will be stored and forward to the combinational circuit. Oh, that really requires some timing, because it depends on really what are the circuits we use really to construct the storage element. So then in that way, really, there is a time delay. So therefore, of course, really any output to be produced really depends on not solely inputs and as well as so-called present state. Whether the present state really is what. So depending on that, really, the next state will produce until you get really the final output. So then that's the key point of really asynchronous sequential circuits. So then if we look at a little bit of a difference between asynchronous and synchronous, so then as you can see the definition. Of course, I have already explained a little bit on that. Internal states can change at any instant of time where there is a change in the input variables. So that means really internal states can change at any time. So depending on the variations of the input variable, depending on so the initially probably 0. So then yes, output really also called the output definitely might be 0, but the next state might be 0 as well. But then depending on the input variable, next is most probably 1, and then becoming next state as 1. So then asynchronous sequential circuits, no clock signal is required. It's not really absolute statement. Sometime really we can use clock, as I told you just before. So then, but only thing is that really, well, what is the ultimate goal out of this actually? Yes, as you can see that in this case, as the memory element, how it works actually depending on really the input variable change, only the next state will be changing. So therefore, yes, this is a good performance compared to synchronous sequential circuit. Why? Because synchronous circuit entirely depends on, as you can see in this diagram, depend on the clock pulses. So then actually, in this case, what is happening that really the output or the next state produced really completely depends on whether clock pulse is generated at the time of really the so that really only the present state will be available to the combinational circuit. So as far as no clock pulse is received, it retains as a stored value inside the flip-flop. So then it entirely depends on control by the clock pulses, while really a synchronous sequential circuit is not like that. Straight based on the change of input variable. So that's what we like. So that's why really, of course, that's better performing compared to synchronous sequential circuits, because the output produced from the sequential circuit, synchronous sequential circuit, entirely depends on clock pulses. So presence of the clock pulses, then only, of course, we will get really the output in the end. So that's the basic difference. So then, as I told you, please don't quote that really no clock signal is not required at all, but rather clock signal might require really from, for example, for the first circuit, or sometimes two different circuits available with two different clock pulses. That means the frequency is different. For example, one is 1 megahertz, the other one is 2 megahertz. So then actually we can really have asynchronous circuits design. So then there is no absolute statement. So sometimes really for the first circuit in the chain of units, most probably we have the clock, but the rest of the circuits are connected without a clock. So then those are the variations we can have. We are not going to go through such complex scenarios, but then we have to understand really how really we really are going to really design this kind of circuits. So therefore, of course, really when really we can use asynchronous sequences. Just for a while, I was telling you that really output is entirely dependent on changing of the input variables, not depends on additional ones such as clock. So then, like synchronous sequential circuits. So then, in a way that really, when speed of operation is important, yes, definitely we should be able to use asynchronous. Sometimes we call as real-time systems as well. So then, we can usually we should be able to use small independent systems, few components. The main reason behind is that, as I explained to you also right at the right beginning, that the output of each logic gate, each circuit really requires some time to produce the output, and that delay might cause really the entire output might be entirely a jargon, because the question is really sometimes the input variable is available, but unfortunately some other variables are not available, are not present, values are not present due to delays that occur. So therefore, of course, really certain conditions. So therefore, of course, as far as we use few components, then yes, definitely this might be useful one. So then of course, when input signals may change independently of internal clock. So that is why it is asynchronous in nature. So therefore, of course, I was also telling you just before that really, when we have two units that have their own independent clocks, so then it automatically works in asynchronous fashion, because two different clocks, and then as I told you, just a simple example is that one with 1 megahertz, the other one is 2 megahertz, for example. I'm just giving you a simple example for that. Okay, so what are the important concepts you should know when it comes to asynchronous sequential circuit design? Yes, as for really combinational circuits, as you can see in this diagram, so x1 to xn, anyway, input variables, and then z1 to zm, sequence the output. So then you can see that combinational circuits as such, no changes will happen at all, but only change we can see is that really, okay, apart from outputs, or we have some delay or storage, that causes somehow really some of the values will be stored for some time, delay, and then the output from that delay circuit will be an input again back to combinational circuit, which might really influence the output Z1, Z2, depending on how X1, X2, Xn change. I believe you would have learned similar ones, probably like multiplexers. So then there is a controllability when it comes to multiplex. Similar scenario you find here, but unfortunately, it is not exactly identical, because the delay circuit means in this case is actually a memory element. Store at some time and then only forward. So then that is why it's called as only a short-term memory. Of course, not exist as such, because this delay circuit might be automatically coming from what we have here, combination of combinational circuits or sequential circuits can be. So we are going to see those really today. So when it comes to short memory, so important concept, we should know that really what is it? Feedback. Output is connected to the input of the circuit. Output is connected to the input of the circuit. You can see capital Y, the corresponding capital Y you find really in the input. Or what we call those capital Y as we call as next state, because based on the present conditions means simple Y1 to YK, simple Y1 to YK, present conditions. For example, Y1 is 0. So all our others are 0. Probably the output is 0. And Y1 also, in that case, most probably as the output is 0. So then it comes with this change 0, 0, 1. So then 0, 1 variable change, and probably then Y1 will change into 1. So then is it 1 or is it output still might be 0. So then sometime, of course, you can see this kind of storing really the present states really matters when it comes to really producing. So then short memory, but then therefore, of course, what we have really two important auxiliary inputs we can call. So then what are they? Normally we call in this case as present state and the next state, because we refer to memory elements. Memory elements always what? Of course, we memorize something today and we will use it tomorrow. That is how we work. So then the intention is very clear. We want to store inside our memory later to use tomorrow. So for something else, today we use for something else, whatever we stored in the memory, and then tomorrow we are going to utilize the information stored inside our memory for something else. So then that is the concept, but this is a short memory. It is not a long memory, like long duration of time, no. So then therefore, of course, we call really this small y as the present state. Present state means really depending on the input values we have in the input variables, there should be some present state, really zeros or ones. So to produce the output, intermediate outputs with intermediate next states. Next states. Normally we call, as you can see, that excitation variable. Excitation variable, that's so-called really next state or big Y. So then in this case, so then the capital Y and simple Y is used. As you can see, that same number of capital Y's corresponding to simple Y's available. So then the important difference in this case is what? Is about really states, next state and present state. Well, that leads really so much of complications when it comes to circuit design, but of course, really very useful tool really for many applications in the actual real world or actual real life. Yeah. Importantly, we have to understand really two important things here. What is that? Yeah. We have to look at it very carefully, as I explained to you just before, that what is that by introducing this delay, if we go back, by introducing this delay, really what is going to happen that really, yes, simple Y1 is not available yet, while X1 has been changed, for example, X1 has been changed. So then in that case, what is going to happen? That might cause really the output really still remains really the previous one up to certain time period. So the expectation is that those delays we must take into consideration means that really we must check carefully whether the states are stable. If the states are not stable, also you have to wait until it gets stable. Oh, so that's really the first. So then when it comes to dealing with asynchronous sequential circuits, make sure current states and next states are the same. Steady condition, steady state condition. Difference between capital Y and simple Y will cause a transition. So then if at all there exists a difference, then we call as a transition. So transition from one stable state to another occurs in response to change in an input variable. Very important. So what is the meaning of transition? Transition is entirely depends on really changing of input variable. As I explained to you just before, x1 previously 0 and will become 1, and that will cause really change of the state, capital Y. So very important, very important. So therefore, importantly, we have to consider this transition from stable state to transition, how it can happen. Okay, so then let's assume you might be thinking, oh, okay, what about changing two variables? Oh, that might cause many issues. We are going to see in short while. So make sure that really when you want to change the state from one to the other, so make sure you change only one input variable. That is the basic concept behind asynchronous sequences, and you must be very careful on that. So then you must make sure that really each state changes really subject to one input variable change. So therefore, of course, really what we call as really when it comes to basic mode or fundamental mode is, as you can see, is no simultaneous changes of two or more input variables. Very, very important. So the time between two input changes must be longer than the time it takes the circuit to a stable state. Oh, that's what I explained you just short while ago. What is that? Change of input you can't do so sudden, because the question is that really change of the state really we have to carefully monitor. For example, let's assume that really with the timing, if you assume that really, of course, the delay goes here in this circuit. So from capital Y to simple Y, this delay, so let's assume like 1 microsecond. But to change really any input variable, most probably we need only half a microsecond. So then we must make sure that really change of input variable x1 really subject to really the stable state of really y1. So then really, of course, that's where really you have to understand very precisely. Time between two input changes must be longer than the time it takes the circuits to a stable state. So we have to make sure that really circuit is in stable state, simple Y is equal to capital Y during really the change of the input variable. So very important. So then the input signals change one at a time, and only when the circuit is in stable condition. So then as far as we follow this, the circuit might not go for, we can call within inverted commas, hazardous conditions. We are going to learn hazardous conditions. So then if at all you violate this, so that might cause some hazardous conditions, inverted commas, but there are many other possibilities that can happen. You will know in short while. So therefore, of course, as you can see that when it comes to asynchronous sequential circuit design, one of the important consideration we do is transition states. Transition state, capital Y and simple Y. Those matters much really when it comes to asynchronous sequential circuit design. So then one of the important table you should know is transition table. Transit, so state changes, it is in transit. So before being produced, the complete output is Z. So then preparing transition table much matters when it comes to asynchronous sequential circuit. But not only that, you have to learn many more tables. Many more tables. Today you are going to learn many more tables and not just this table. So then in that way, of course, really transition table determine all feedback loops in the circuits. Mark the input Y1 means simple Y1 and output capital Y I of each feedback loop. Derive the Boolean function for all Y's, what you would have done in combinational circuit. Plot each Y function in a map and combine all maps into one table. Circle those values of Y in each square that were equal to the value in Y in the same row. So these are the steps you have to follow to get really done really transition table. So some of them are quite easy for you because you would have already learned. So then, for example, you have this circuit, and then you know how to really get, I'm pretty sure, capital Y1. So Y1, so you can see, so then I hope that I don't need to explain that. So then you can see here is XY1 really is one AND gate, right? But then also it goes to the one NOT gate, and with this through this, and then get rid through this OR circuits to produce XY1 plus X bar Y2, X bar Y2. So that is quite easy, X bar and Y2, I hope really. Y2 is equal, so the bottom one. So then that really depends on these two again. So, but in this case, really, of course, you can see Y1 bar and then X directly. So then X Y1 bar plus X bar Y2. So then that's really what we have. Two important Boolean expressions. So then we follow this. So then derive Boolean we have done. So then now we have to plot. So then when you would have learned like most probably a truth table, or sometime we can call, of course, probably you learn also Karnaugh maps. So then similar things, of course, you do, you know that really whatever be really the case, really when it comes to rows and columns, we just put really such a way that really from adjacent rows really change only one bit, not both of the bits in case you have more than one bit. So then in that case, for example, so Y1, Y2, as you can see, 0, 0, 0, 1, and 1, 1, because 0, 1 to 1, 1 really change only one bit. As you can see, 0, 1 only change. The other bit remains unchanged, and 1, 1 to 1, 0. So then instead of 1, 0, and 1, 1, you might know by now. So Y2 is same way we can draw. So then transition repair table we prepare. So then by putting these two, have really so-called capital Y1, Y2 here, as you can see. So then in case of capital Y1 here is 0, 0, so therefore 0, 0. So then 0, 1, so that means really here 0, 1. So then, of course, like that, of course, you can really see that really, of course, we have. So then one of the important conditions, really, one of the important conditions when it comes to this transition table is that really in any of the rows, really, you should have at least really one present state, really, 1% state, any of the squares or any of the cell. So you should have one. So like, for example, here, present state is 0, 0, next state also 0, 0. In this case, 0, 1, and then we have a 0, 1. 1, 1, we have 1, 1. So then those are the ones really, of course, circle in this case, as you can see. So then so make sure that really you have really somehow one of those cells really with a present state. So then in that way, of course, we can obtain the state table, depending on really present state, we can get really the next state. So then more or less this table, we can really map into this kind of table. Why? Present state means what? Y1, Y2, 0, 0, 0, 1, 1, 0, 1, 1. Of course, you must be very careful if you put like this in the table continuously, then you have 1, 1 here. So then when x is equal 0, so when x is equal 0, so then what are the next states? This is what? When x is equal 1, what are the next states? Those are the things we follow. So then, as you can see, that really is, yes. So then usually you can see, as I told you, at least one next state entry that is the same as the present state. So then that's how really, of course, you get transition table. So then in that manner, of course, really, you should be able to do really a transition table for any type of circuit. Any type of circuit really we are planning to. So in this case, if you look at it, what we have in this case, basically what we have really, of course, a very simple circuit, not much complex, quite easy to obtain. But then there are more complex circuits that we have to look into. So then very similar really in this case, of course, this is an SR circuit. So usually sometimes people call a set and reset. So then set and reset. So then conditions really, in this case, you can see that this set reset or SR circuit really is drawn using NOR, NOR. So then, of course, really, then we can get the truth table depending on really. So importantly, you can see that R with the NOR gate connected to Q, and then S with again NOR, of course, feedback from Q is really Q bar. So then you can see that importantly, if Q is equal 0, so Q bar should be definitely 1. Am I correct? So otherwise, it is not a stable condition. So as far as Q and it should be really, if at all, really it's Q bar. So then in that way, of course, really we should have some initial conditions, but the expectation in this case is really, of course, as far as, for example, R remains 0, so then if at all Q is equal 1, the expectation is really independent of the value of S, Q should retain unchanged. So because we are resetting the circuit, reset. So reset means really reset is pushed and then set, whatever the values do not imply anything. So on the other hand, in case of set, so then as far as set is pressed, so then we should have really then the Q change, because now the state is changed. So therefore Q has to be changed. So that's how really you can see this truth table has made. So then you can see initially Q is equal 1. So then Q is equal 1, and then S start from 1, 0, start from 1, 0. So then if at all really, as we now understood, only one input variable can be changed. So then S is changing, but R is not changing. So then 0, 0, for that conditions also Q should retain unchanged. So you can go through the circuits, of course, really, and then you can get it. I'm not going to go through all of them because we have no time. So then when it comes to from the second row to third row, of course, again, we must make sure that we change only one variable. So then we can see here, we change S from 1 to 0. So then R really 0. So then now S we can retain unchanged, and then we change R into 0. So then the expectation really, of course, in this case, yes, retain Q really as a 0, because the question is set condition. So the set button is pressed. So that means Q S is equal 0. So but R can change from 1 to 0, but Q you can see retain unchanged. So then, but only thing is one last condition we have. Of course, really you can see that, yes, from here to 0, 0, and then of course we have not considered really 1, 1 at all. So then that's really, you can see that causes really some sort of an uncertain condition 0, 0. Okay, so then having said that, so yes, in that manner, of course, really you can really look at it how you can get it by analyzing, because you are very well aware about really how the NOR gate works. So then please do so. So then we can see that we have really circuits showing so-called feedback, and then you can really look at it as well. So then I'm not going to go through in details. Better you really practice at home and see those. So then when it comes, if we can also construct SR using NAND gates. So then in that case, how it works. So then please go to. But of course, practical application of this, as I told you just short while ago, of course, really, as far as really we have this connected to A, so then that means really S is equal 0, because this is connected to the ground. So then simply really we are really connecting to the A point, we are connected to the ground. That shows really here we have 0. So then if we connect to B, that means really R will be 0. So then in case really when you really move this one from A to B, that means really we are changing really from S0 to B point is 0 because connected to the ground. So S becomes 1. So then that leads somehow bouncing conditions. So then, of course, the expectation really, of course, to retain in B disconnected, so that really we have to get ready for debouncing. So these are really the applications, but we will see those applications, of course, not really during a practical class. You can observe that, so that really, yes, you understand perfectly. But otherwise, of course, you can read and see and then understand how it works. So then, in order to design asynchronous sequential circuits, as I told you that really we need many other tables. So one of the fundamental table considered as really so-called flow table. The idea behind the flow table is that really, yes, it is exactly transition table, but only difference is that really replacing whatever bits by later symbols. So that's the whole point. So that really we have really somehow different, we can call states using really letter symbols. So that might really really perfectly good for us, because then to understand, like for example, you can see that here many zeros everywhere. So then instead of this 0 0, if we have A, oh, then we perfectly know that this is A state. So then likewise we have A B C D. So then we should be able to understand. That's more or less, of course, what we have done here. What is that? Of course, really here's the same transition table. We have put wherever 0 0 we replace A, wherever 0 1 B, wherever 1 0 Z, and then D 1 1. That's really what this author has done. So then on top of that, of course, really you can also mention what is the output. Output means Z. Output means Z. So then all the time output is 0 only when B is equal 1, and then x1, x2 both are 1. So then only B becomes 1. So then the output also you can just, in this case, of course, what you have really 2 inputs and 1 output. So then 2 states with 2 inputs and 1 output. So then in that manner, of course, really we can really put so-called we can say that we can map so-called binary values into really so-called letter symbols, so that we understand perfectly. Yeah. So that's the whole point. But anyway, you should know very well that. So then in that manner, of course, we can get really so-called flow table. So then how to obtain the flow table? Of course, assign to each state a distinct binary value. So then obtain circuits from the map. So that really, of course, whatever the states you have, really we can convert into binary values. Make sure that if we have 4 states, so then we need really 2 bits. That part you know very well from combination circuits. So that really later on we can obtain the corresponding combinational circuits. But of course, there are really 2 important or 2 critical difficulties that might present in this case. The output might be assigned to an unstable state, or binary state assignment, really, of course, subject to the race condition. What are those? So then that's basically what I was telling you before. Of course, so then in case risk, what is the meaning of race condition? As you can see that two or more binary state variables will change value when one input variable changes. Oh, when one input variable change, two or more binary state variables will change. Two or more binary state variables change. So then that causes race condition. So then cannot predict state sequence if unequal delay is encountered. That's what I explained to you. So then what is that? In case really the delay cause really is kind of a 2 microseconds from the delay circuit, but for every half microseconds input can be changed. So that delay might cause really subject to again what we call as unstable states. So then that's called as really race condition. So then race conditions, there are two different types, non-critical race and critical race. So then non-critical race is quite what we can cater, not a problem. Of course, really we should avoid. The final stable state does not depend on the change order of the state variable. So final stable state does not depend on the change order of state variable. For example, when it comes to really this, of course, really final state table, final stable state does not depend on really the change order of the state variable. So then it does not depend, because you can see state variables are changing, but of course, finally, what we get really the state we can call stable state. But of course, when it comes to this table, what we can see, so then 0, 0 to 1, 1, and then 0, 1, we produce really, of course, 0, 1, and as well as 1, 1. So then 0, 1, 0, 0, 0, 1, and from 0, 0 to 0, 1, and then it produces also 1, 1, and then from 0, 0 to 1, 0. So then also we can see that the change of the state still produces 1, 1. So then state table, final stable state, 1, 1, of course, does not depend on the order of the state variable change. So then similarly, you find those are really possible transition. But in case of critical race, the change order of state variables will result in different stable states, should be avoided. Oh, so change order of state variables, 0, 0. So then you can see it leads to 1, 1. But then 0, 0 when changed to 0, 1, of course, really you can see that really what we get really. So then in that way, of course, what we can see, different stable states we obtain really when the change of the state happens. So then that's we should entirely avoid. So that's the whole point when it comes to critical race and non-critical race. Of course, we have to look at examples for that, but this is just a kind of abstract example just for you to understand. So then non-critical race, of course, we can still have, we can still present when it comes to circuit design, but critical race we should avoid all the time. So then so therefore, of course, really the expectations, so these usually the race conditions you can avoid by proper binary assignment to the state variables, and that really leads no much problems when it comes to the race conditions as such, so that really there will be no issue. So then expectation is somehow really when it comes to preparation of the flow table, if you prepare really binary assignment state variables so that really state change really from one to the other by changing only one binary value, so that really, yes, then there will be no. But of course, still really we have to see some critical examples really to understand that. So then, therefore, if at all really we want to look at it, so then the expectation really of asynchronous circuits always really what is the stability check, as I explained to you right at the beginning. What is that? Of course, when it comes really due to the feedback, and then such feedback really delays that occur, most probably might lead to really unstable states. Despite you have changed one of the input variables, that does not reflect as such, really, together with really input state means simple y1. So then of course, really, yes, we have to see that really those are considered as unstable. So then in that manner, of course, really you have to really look at it very carefully. So then what are the conditions that produce really unstable states? So then any column, really, if you see that really has no stable state, we consider as really unstable. For example, in this particular circuit, again, I'm not going to explain all of them. If you look at really these are two rows, we are looking at columns. The expectation is what? Of course, really change of one of the input variables, from one column to the other. So that really look at really the state changes, for example, in Y. So then you can see that here is 0, 0, here 1, 1. But when it comes 1, 1, of course, you can see that we have two different states. Here, when it comes to really 1, 1, this y change from 0 to 1, and then in when it comes to y is equal 1, change into 0. So that means really next state has been changed, really. So that really y and capital Y and simple Y are never the same. So then in that case, of course, really what we have is really unstable states. So then the expectation is, then you can see that when it comes to if you properly derive the transition table, so then in that case you can easily monitor what are the unstable states. So then in that manner, of course, really you can see that the unstable states in this case will be, yes, you can see that when x1, x2 is equal 1, 1. Okay, so then stability check is very important when it comes to asynchronous sequential circuits, as I told you. So then make sure that really stable state is there all the time before being changed, really x1. So that's why longer duration is required. Longer duration is required all the time, really, for x1 to change into another value, because y1 take little time because of the delay, feedback delay we have. So then we must make sure, really guarantee that. So you have now fundamentally, we can call that basic background, really, to go for designing asynchronous sequential circuits. So then, similar to combinational circuits, so you can see that what we have here, 6 steps, and then you have to follow these 6 steps really to come up with a complete asynchronous circuit design. So then there are a few tables you have to understand. So then today I might not be able to really give you any examples by any means, but of course, only thing is I am going to explain slowly about the tables. So the table, so that you understand perfectly how the table works, so that really you can go for complete design probably in a practical class later on, or tutorial class. So then, yes. So one of the important thing, of course, really, first of all, you should understand very well the problem. I mean, you should define. So then in this case, mainly about states, the design specification. So then importantly, yes, we have internal states, we have really internal states, present state, next state. So very important. So then in that case, we have to understand. So then from that, we try to interpret from the design specification. We have to interpret. So then in order to interpret, the first step towards which is that to obtain primitive flow table. So I was explaining you just for a short while ago is flow table. Flow table, that is essential. And then the next steps towards it, of course, the primitive flow table. It calls primitive. Primitive flow table is subject to having many states, sometimes redundant. Some states are redundant, not required. Oh, we cannot call as redundant, rather we can simplify. So then reduce flow table by merging rows in the primitive flow table. Oh, for that, we have to use two important, we can call concepts: implication table and merger diagram. So then one is a table and other one is a diagram. So then reduce equivalent states and compatible states. So what we reduce is equivalent states and compatible states. So we have to identify, we have to understand what are the equivalent states and compatible states. So then we have to assign binary state variables to each row of the reduced flow table to obtain transition table. So then we have to really assign binary values, then output assignment, assign output values to the dashes association with the unstable states to obtain the output maps. So then dashes automatically implies, you know very well, that really no proper, we can call value. So then 0 or 1 probably normally we can call also, of course, don't care as well. So then we can simply draw the logic diagram. In this case, so we can see based upon really the transition table we obtain, so then we can go for the design. So then we can see one of the, a simple example. So then gated latch. So the expectation is that really the output Q is always equal D when G is equal 1. Q retain its value when G goes to 0. So then D has no effect. So then this kind of really we can call as a buffer or as a memory element. It's just really pass through the value and that's all. So then, yeah, so then how many states really we can generate out of this is matters. That matters. So then, for example, so then you can see that when G is equal 1, Q is always equal to D. So then, so you can see then first two combinations really says G is equal 1. So then D can change. Really, of course, Q reflects all the time as the output reflects really whatever available in. So in a way that really G really just, if G is equal 1, whatever values in D will be in the output. So input D will be automatically reflected in the output. It is a kind of a delay circuit, or we can call. So then of course, really, in a way that really, of course, then later on, yes, we have to really change really D, and as well as, of course, really now G was 1. So when G is 0, what is going to happen? Of course, really, that's what we have to see. So then in that, what we understood previously is that as far as when G is equal 1, always D will be reflected in Q. When G is equal 0, so then in that case, what is the expectation is that really, of course, the value we should get really independent of the value we have in D. So because G is equal 0, so then Q should be, output should be 0. So because the question is really G really governs really the propagation of D input into the output. So then, of course, really in that way, of course, you can see further two below conditions. Of course, you can see G is equal 0. So then D will change from 1 to 0 and then 0 to 1. So then you can see that really what we get really output as 0. So then in a way we change really from so then G, while G remaining 0, so then we change D into 1. So then, of course, really the expectation is now is, of course, what we can see as really the output really as 1. So then, in a way that really, of course, D in this case is 1. So therefore, of course, really it's Q start from 1. So therefore, of course, really no matter D changes to 0, still retaining 1. So you have to understand that really Q is in this case, of course, really you have to see that really as a feedback. So then in that way, of course, really what we can see that really these last two is you can get really after state B or F, what we get. So after state E, so then we get really in that way, of course, really we can call as really uh, the table prepared, so that really we can go for really the tables such as, for example, flow table, uh, and implication table, and so forth. Of course, we should be able to really derive out of that. So then in that manner, of course, we can really look at it all. So then only thing is, of course, you have to understand that really once you really fill it, so then the flow table, so then you can see that in this case, when it comes really first row, of course, what you have really as a stable state, really what we can call as only one. See, each row, what we have as a stable state is one. B, C, and D, in this case, E and F. So that really, here's a primitive flow table. Only what we have is one state, one stable state. So then, so as you can see that what we have here, input DG. So input DG. So then, of course, you can see 0, 0, 0. So then we have A, B, C, D, E, F. Of course, as you have noticed here. So then, of course, output varies depending on really the states. Of course, really, then you can see. I mean, I will go through only one row. So then later on, you should be able to see that, or you can do it yourself. So then, 0, 0. So then DG 0, 0. So then DG 0, 0. So then here is 0, 0. Correct? 0, 0. So then 0, 0. So then what we have really in that case, of course, you can see two equal states, so equal input variables. So then instead of really having both, of course, what we can really draw is that really, of course, we can put C, comma, of course, really what we have is optional. Optional means, as you can see, in this case, what we have as really the output, of course, really, you can see C is 0, and then the output here is 1. So that means really between C and F, what you see is that simple change only in the output. So then input variables are same, no changes. So that really there will be no changes. So then C and F we can consider in that form. So that really yes, I mean, we can consider as, for example, in this case, what we can see later on, we will understand. So then how it looks like. So then likewise, of course, you can fill. So you can see that A, 0, 0, 1. So 0, 1. And then let's see really, of course, really, yes, 0, 1. So then what we can see is that really 0, 1. So then in that case, we don't have any 0, 1 here. Am I correct? No 0, 1s. So only this. So then output is 0. So then therefore, of course, really what we have is A. So that means A state retains unchanged by changing 0, 0 into 0, 1, a stable state. So then likewise, you should be able to fill the rest as well. So then 1, 1. So then I will go only one more. So that's really 1, 1. So then do we have any? So then, of course, really in this case, what we have is that really B. So then in that manner, of course, really you can fill the table respectively, of course, with that. So then in that form, if the present state is A and the next state is so-called B, so then what is going to happen? Really, of course, we have to indicate. So then in that case, really what we have is here. So then in this case, of course, what we have is present state is A. Sorry, present state is A. And then if at all really 1, 1, what is going to happen? Of course, what is going to happen? Yes, what we get is really B, but the thing is that really Q change from 0 to 1. That means really Q can be really any of the values, 0 and 1. That's where really we put as don't care. Also, of course, we can take. So then that's how really you can fill. So then 1, 0, or of course, because 2 in that case can be any state. So then therefore, of course, I will go through that one as well. So then while we are in A, so then if at all DG becomes 1, 0, so then what is going to happen? That really what we have here, you can see that really 1, 0 means these two. So that means really can take D and E, and then also value change, the output change also to 0 and 1. So therefore, of course, both are, you can see that they don't care conditions. Yeah, so in that way, of course, you can fill, and then the as you notice that really in each row, what you have really one stable state. So then you see here B and output is 1. So then here output is 0, here also 0, and then here E also get output 1, and then F also get output 1. So then when change really from one state to the other, based on really the input change, of course, we have to find out really how to fill really the flow table based on that. Of course, you have to do. So then when input changes, what happens to the current state or present state? Sorry, what happened to the present state? What is the next? So then that's what we have to do really to get ready really primitive flow table. So then once we get primitive flow table, the next step will be how to reduce number of rows. So then, as you can see that state reduction, the expectation is the state reduction, reduce flow table by merging rows in primitive flow table. So we have this primitive flow table. Let's assume that you have already filled all of them. So then how to reduce this? So then the expectation really is to reduce number of rows. So then by reducing the number of state variables, by reducing the amount of logic required. So then what are the mechanisms we normally use? Of course, equivalent states. So one is called can be combined by using implication table method for completely specified state tables. Very important for completely specified state tables. Equivalent states. What are the equivalent states? So we can really find out equivalent states looking into really dependencies and so forth. We can see compatible rows can be merged for incompletely specified tables. If the two rows maintain really the same dependencies, so then of course really we should be able to really merge those. So we will look at it really using an example. So then, of course, we can see that really this example really, of course, I don't want to touch this one as such first. I want to touch really this one first, because then you understand perfectly how the implication table we can derive. So then you can see that we have to look at it. Yes, don't care conditions, and some really we have don't care conditions, as we found out really in the flow primitive flow table. So then this is the primitive flow table we have. How we can get really implication table? So that's the important one. So implication table, what we have really, each square of the implication table, you can have only we can call really 3 things. So of course really dependency, such as for example D comma E is a dependency. So then X, so then tick. So we will see what are those. What are those? Of course. So then we will go row by row, because our expectation is what? Reduction of number of rows from one side, looking at really equivalent states, and then at the same time later on compatible states as well. So then let's see what we can do. Right. So for example, so then the implication table is drawn like this, B, C, D, E, F, because we want to compare first row with the second one. So likewise, you can see that really what we have really in the horizontal direction, what we have A, B, C, D, and in the vertical direction, we have B, C, D, F, because we compare first row with the subsequent row, one row with the other one. So then we have that. So then A row with B, A row with B. What we have to see that really what are the dependencies? What are the dependencies? For example, we look at really column by column. So column by column. So then you can see that input value is 0, 0. So then A to B. So then we can see that here the next state is C, and then don't care. And in B, what you have is 2 don't care. Of course, then that means this perfectly matches, because we can put really the first don't care C. Also, that means it is completely compatible. Am I correct? So then the next one, you look at the next column, when input values x0 and 1. So then A, comma 0, A, so that means the next state is A, and the output is 0. But when it comes to B state, so column wise, yes, next state is A, but of course the output can be either 0 or 1. So therefore, of course, really, they are both these 2 columns are also perfectly matching, both these squares. We are comparing A and B, and then likewise you do it for B. A change to B when input variables change to 1, 1, and then B don't care, and then here B, comma 1. So then this don't care we can consider as 1. So then perfectly compatible. These 2 perfectly compatible. So then similarly A 1, 0. So 2 don't cares, and then here E, and then of course completely compatible, because this don't care we can consider as E. So therefore, you can see that A and B rows are completely compatible. So that is why we have really tick. We have a tick. So then we go one by one. I go really with another one. So then hopefully you should be able to do. But anyway, I will go, of course, about 3, 4, of course, because there are 2 here and so forth. Let's see. So then A and C. So row A and row Z. So then, of course, I'll go a little bit fast, this one. So then you can see here, A and C, so fully compatible. I hope you got immediately, because C, and this one also C, 0, of course, can consider A, of course, B, it is also B, and then, of course, all are compatible. That is why, tick, completely compatible. So then we have to go. Now we have looked at A and C, but I want to look at now B and C. B and C, BC, of course, you can see BC. What is going to happen? BC, yes. So, of course, the first one, so you can see, of course, completely compatible, no problem. A is completely compatible. This one is completely compatible, but unfortunately, this one is not. So that's really, you can see there is a dependency. So then between B and C, there is a dependency. Merging B and C entirely depends on D and E. Oh, so then therefore, of course, really, yes, what we really wrote down here is D, comma E as a dependency. So then reducing B row with C is subject to the dependency, D, comma E, subject to the dependency. So of course, by having dependence, it does not imply that we cannot reduce. We cannot merge. That is not the case. So don't expect that really X will come here because of that reason. But later on, we will see that reason alone. We will see later. So then likewise, of course, I will go by really this one as well. There are 2 dependencies, C and E. C and E. So you can see that here is C and then here is F. So then we have a dependency, CF. So, but of course, this one is no problem. C, second column, so no problem. So third column, 1, 1. So you can see also no problem. C and E, no problem. But then the last column, D and E. So then we have a dependency. So there are two dependencies. There are two dependencies. If at all we want to merge C and E, subject to two dependencies, D and E and C and F. So likewise, of course, I hope that you can fill up really the implication table. So then from the implication tables, what we are trying to get really the number of rows reduced somehow, so that really, yes, what we do later on, of course, from the implication table, now we get really so-called really rows which are 100% compatible. First, we write down what is that. Of course, really what we can see is that really this one, right? This one, all ticks we can write down. So A comma B, A comma C, A comma D. You can see all these, right? So then B comma E, B comma E, B comma F, and then what we have here is C comma D and E comma F. So then, so therefore, of course, really, we have really gotten really out of all ticks. So then, now what happened that really, we have to see this C and D rows, of course. So you can see that really when you look at really C and B, of course, we have C and B, of course, D, E, right? And then we have really B and D, of course, we have D. So only thing is that what you can see is that really by now we have really all we have really, of course, really all other compatible rows, A, B, A, Z, A, D, B, E. So then therefore, of course, really we don't need to consider D and E anyway. So then therefore, of course, really there is no need really to look at it. But for two reasons as well. Of course, really when you look at really D and E here, when you look at really B and BC, of course, really this one is of course optional. So then there is no problem. So then when it comes to B and D, what we have is D comma 0. So then when it comes to another combination, so of course really C and D and E, of course, what we have really 0 and 1. Oh, very important. Another important conclusion we have to reach as well, that in any point, of course, really in the transition table, if you have two different outputs, so then for the dependency what we have, that leads that really that entirely we have to discard. So there is no mechanism really to what? To reduce, because two different outputs. So then from that itself, we can conclude that really D and E dependency really makes really trouble to reduce the rows. So then similarly, you can see with C and F as well. So you can see C and F, here is 0 and then here is 1. And that leads that really we have to cancel out really the reduction of rows based upon these two dependencies. So very important, but by any means, really the output is same, then we have to still consider really that dependency for the reduction of rows and of course equivalent states and as well as compatible states. We have to look at it in that case. But in this case, you can see that yes, two different outputs produce for two different, the rows we have already looked at. We want to really merge, but unfortunately output is different. One is output is 0, the other one is output is 1. So we have to discard. There is no mechanism to reduction those two rows at all based upon the dependency. So therefore, of course, we have to discard. Very important. It is not that really because we have all ticks and then all other dependencies we have to discard really as really no way to reduce. No, as I told you just before, in case here was D0 and then here also so E0, most probably output is same and then We have to look at it, whether we can go for equivalent states and compatible states or not. So then we have to look at it, examples for that. So then once you obtain uh, we can call really these uh, uh, dependencies, normally we call as dependencies. So then sorry, not dependencies. Actually, in this case, of course, what we have really A comma B means really they are completely matching, completely compatible. A, B, completely compatible. The expectation is to really now reduce really by replacing B by A, for example, something like that. But how do we do? Once you get the implication table, that does not imply that really you can straight away do, because you should be able to still minimize, because you have so many, you can see so many compatible states. Now we have to look at it really how to minimize this using what. Of course, we can do really that, looking into really how we can really go for maximal compatibilities using so-called merger diagrams. So you initially use implication table from flow table, and then later on, of course, once we get compatible states or compatible pairs, so then you look at it maximum compatible by using merger diagrams. So merger diagrams. So we will look at it, merger diagrams. Of course, the merger diagrams we will see step by step, rather looking through really all these conclusions. I just want to go for the merger diagram first, so then come back really. So then we will see really how we can do first. So then you can see that, yes, this is an example. This is an example. So they're not that really the example really coming out of really what you have seen just a short while ago. Two examples given just for you to understand first. So then you can see that first diagram. So first diagram, of course, we have really, we have really, of course, we have these compatible states. So then AB, AC, AD, BE, BF, CD, EF. What we do really in the merger diagram, of course, really, we connect each of these really using a line. A with B line, A with C align, A with D is aligned, B with E is aligned, BF, CD, EF. So that's what we can see here. So then that's what you can see here. So then we have connected really all using lines. So then first thing is to do that, taking into consideration really compatible pairs we obtain, we connect using lines. So after you connect using lines, so then of course we have to find out minimal collection of compatibles that covers all the states and is closed. Oh, very important. Minimal collection of compatibles. Minimal, not maximum. Same as really what you would have understood when it comes to so-called Karnoff maps, if you would have done, I don't know, that covers all the states, but should be closed. Oh, what is the meaning of this closed? We will see. So group of compatibles that contains all possible combinations of compatible states. Group of compatibles that contains all possible compatible states. So can be obtained from a merger diagram. So line is the diagram represent that's two states and compatible, compatible. So then importantly, not just two states only compatible, like what we got really pair of states, but you can have really more than two. Oh, if you have more than two, oh, how do you get really those n-state compatible? Oh, it says very clearly, n-sided, fully connected polygon with all its diagonal connected. For example, if you have a rectangle, how many diagonals we have? Two diagonals. So then all must be connected. Fully connected. fully connected. So then we get really n-state compatible. N-state compatible. So then the idea is very clear. Now you have to understand, and after you connect using lines, we have to produce polygons closed, and at the same time, all polygons we define there, we identify there, should be fully connected. Means all diagonals must be connected. Then only we can consider as really in-state compatible. So then therefore, of course, really, if you look at it, if you look at it, so you can see what? Of course, you first impression, you have to look at it, polygons. How do you identify polygons out of these connected ones, out of these connected lines? So you can see that, you can easily see ADC is one triangle. Oh, triangle has a diagonal? No, triangle has no diagonal. So then triangle, and then second triangle, what you see is BFE. Oh, then what is the conclusion? Oh, these three states in each triangle considered as three states compatible. Oh, what we got really from implication table, you can see that, so just pair of states as compatible. But now we can see that we can maximize really compatibility of states, just not really 2, but now increases into 3. But again, you can see that it is reduced to A, C, D, and B, F, this one. But then we have AB. Oh, very important. So AB is also, then we have separately connected. There is no triangle corresponding to it. But of course, we have to see one of the important statements. Find a minimal connection of compatibles that covers all states and is closed. So then we will go slowly one by one. But of course, the second example given is really for you to really go through, without looking into really the examples we have already taken. So then, therefore, of course, really, yes, that one really you practice at home. So then in that manner, of course, really we can say that really we have now, what we have really now is what we can call as really we have reduced into 3 rows. That's what we have: AB, ACD, BF, because we have found out that really they are all compatible. They are all compatible. So then, but when we have really, then we have another conclusion we can reach. What is that? Of course, the closed covering condition. So then the chosen set of maximal compatibles must cover all states and must be closed. Include all states of the original state tables. No implied states. So implied states are included within the set. No implied states, or implied states are included within the set. So therefore, of course, really, when it comes to A, B, actually A is included in ACD triangle, B is included also BF triangle. So then actually, there is no need to really have so-called that really AB in this case. So therefore, we can easily remove. Closer condition is satisfied. So therefore, of course, really we don't require. But not all the time it can happen. So then in this case, yes, that is possible, because you can see that we have included A states really in the closed triangle, and B is included also in the closed triangle. So then this is not a requirement. But in case we have a separate line, for example, no, like in this case, what we have is really G separately. So you have to put G. So then likewise, of course, really, you can find also CD. Oh, of course, CD is also, you can see CD. So not included in the triangles and rectangles. So in this case, A, B, E, F. So very important, G is separate, and then C and D. Oh, D is really entirely separate to the polygons. So then, of course, really C, D is considered really as a separate compatible. state. So that's very important. Here we can remove AB because of the, as I told you just release. So then in that way, of course, we can really come into final reduced table, of course, by replacing so-called, you can see that ACD. So ACD, of course, here I bring here really only ACD rows, not others. ACD is all are compatible. If all are compatible, C and D all can be replaced by A. So that's where really, of course, really ACD become A, and wherever CD becomes also A. And then in case of BF, as you can see that really BF are compatible states. So therefore, of course, we can replace all E and F by B. So that is how you can see that we get in the end really so-called reduced table. So then in that manner, of course, really you will be able to. So then, of course, you hopefully you understood, of course, very, very important. So then there are some other examples. Please go through and then try to understand. And then importantly, the subsequent slides. Yes, I'm running out of time. Of course, to understand, as I explained right at the beginning, race-free conditions. So avoid the critical races. So then, as I explained to you, of course, really is very important. And then to understand the condition, of course, you know very well from combinational circuits, adjacent variables only we change only by one bit, not both are really variables. In case of two variables, so we don't change. So that's very important. So then in that manner, of course, really you can find out a few other examples. Of course, I have no time to go through all of them today. So then in that form, really, of course, we can design race-free asynchronous sequential circuits which have a timing diagram. So then in that case, what the expectation is really, so the timing to be really always to be considered in order to really make sure that really it doesn't enter to a race condition. So then that's what I explained at the right beginning. So in that form, of course, we can have really all tables from one side, of course, really first one really what we get really the state diagram, and then primitive flow diagram, and then using primitive flow diagram we can get the implication table, as I explained to you one by one, and that is quite important to understand. So merger diagram and implication table are really fundamental. So of course I don't say that really others are not really fundamental, but of course if you don't know really this, definitely you will not be able to of course go through really the circuit design. So in that form, of course, I think my time is up, or I have more time. Hello?
Yes, you can, sir.
Pardon?
Yeah, we can add 10 to 15 minutes for time.
Oh, that's okay. I thought really I cannot.
If you want, that's okay.
Okay, that's why I want to go through it. Of course, a race condition and race-free circuit diagram, of course, most probably you might need to explain during.
Yes, I will explain further in the class for the race and how to avoid the race condition.
That's right.
That's okay.
That's perfectly, I believe, fine. That's always about really the timing, and that's very important. So then I have already explained fundamental tables. That's very important for students in order to design the asynchronous sequential circuit, and that's clearly important to go through step by step. So primitive flow diagram, and then later on, of course, we can really go for implication table and
reduce states or something.
Yes, merger diagram. So this is really important in this slide set. But of course, importantly, lastly, of course, explains about hazards. So then that's also very important to understand. Yes, that's always really because of really what I explained at the right beginning. So if at all so propagation delay, so in different parts, that may cause really, of course, the malfunctioning, or means false output, we can say. So the output is false because the question is really previous state has been used really to produce the output, because the present state has not been changed based on really the next state produced in the previous combination. So then while changing the input variable, that's very important to understand. So then in that manner, of course, what is going to be some kind of hazard conditions, so that causes due to the mainly due to different propagation delays in different parts. So then in that leads really you can see that false output values in combinational circuits, because in the end, simple y with x input really produces the y next state, and that's entirely about combinational circuits. But unfortunately, the delay might occur really to present the value, particularly coming from the delay circuit or feedback, as I explained to you, memory, and that really causes these different types of hazards. For example, in this case, really you can see static 1 hazard. So then, and this one is static 0 hazard, and then this is dynamic. So that means it is fluctuating entirely. So then from 1 to 0. So these three hazard conditions can produce depending on really the delays about hazards you can go through. So then question is, in this case, yes, why the particular output has not been changed based upon really the input and as well as what we call as really a feedback produce. So then in that manner, of course, you can really understand different types of hazard. So this one basically going through really taking into considerations the variables and change of the variables and how far it is delayed. Just give you a little bit of explanation. For example, no, x1 is equal 1 here, and then straightforward for this AND gate, there is no problem, no other gate involved. So therefore, really x2 is also present to 1 immediately. There is no delay. But unfortunately, when it comes to AND gate number 2, you can see it goes through a NOT gate. Additional delay in producing output from NOT gate. So then that might cause, because that is where really the propagation delay might occur, because in this particular path, it is very smooth, direct connection to the AND, but in this path, there is no direct connection, it goes through a NOT gate. So additional delay. So then, so that causes most probably the erroneous output, really. So then, therefore, of course, really, you have to. So this is called static 1 hazard. So then, of course, you can use really NAND circuit as well, and then see really whether that static 1 hazard produces or not. So then, because you know that NAND gate really is completely constructed, so then therefore built-in available, not like NOT gate. So this NOT gate would have also replaced by a NAND gate, actually. So then, yes, static 1 hazard is yes, is because of that reason. For example, yes, that's so then likewise really we can get really, of course, other hazard conditions. So the hazard free circuit you can produce by introducing some kind of redundant gate and so forth, and depending on really what kind of really delay you have to use in order to be available the correct output. So what kind of delay to be introduced due to, as I told you just before, is NOT gate and so forth. Okay, so then in today's class, what you learn is sequential circuits, but of course, very particular sequential circuit, asynchronous. So then race conditions, so very important to understand. So then now, of course, you understood what is a race and what is a hazard. Probably someone can answer me what is the difference between hazard and race. So that one is very important. Okay, I can see a few chats, and what are those? Any questions?
Yeah, any questions about from Dr. Arosa's lectures today? No?
But importantly, you should know very well
Yeah.
table, table, merger diagram, they are really important. So then without those really
maybe a bit simple question from me. Usually, what is for this kind of application? Usually, say asynchronous circuit is not the maybe a synchronous circuit is preferable in this time and age, yeah, especially if you are controlling something with an SoC or a microcontrollers. Now, the what I want to ask is there any advantage of this asynchronous circuit design in the application?
yeah, actually, this is a very good question. But I have very simple answer for that. Of course, synchronous circuit is preferred. There is no absolute doubt on that. But there are sometimes there might be. I don't know whether you realize that really when it comes to some kind of microcontrollers, they use really some simple keyboard.
Yeah.
Simple keyboard they use, very simple. And then most probably any of these ASCII characters really, you know that it goes through a shift register.
Yes.
Shift register. But by no means actually shift register is not sufficient really to shift register alone is not sufficient. But if you have shift register, you know that really anyway you have really clock there. There is no doubt on that. But only thing is that there should be a buffer between shift register and the processor, because the moment really you produce really, because you know that from the keyboard, most of the time the key press really goes in serial, bit by bit. For example, I think simple A is, I believe, 40 or 41A, something like that. Oh, I can't remember, but something like that. Either capital A or 41, what I remember. So then, but it doesn't go as capital A, it goes at, you know, first 0001 and then later on 100, correct? But it goes serially and then produces parallel based on the shift register. You got my point?
Yes.
But then from the shift register, flushing into the memory is not done by actually
pure
directly from
sequential.
shift register.
Yeah.
But you need a buffer.
Yes.
Store and forward. Store and forward. And that one ultimately not required clock.
There is the asynchronous sequential buffers. Yeah.
That is one of the example what I can see. But still, I can see that really still you can use a synchronous circuit. But only thing is that they use this so-called buffer, not using a clock. Rather, they use third state buffers. Third state. 0, 1, and third state. So open means really the resistance
tri-state. They use tri-state buffers. Yeah.
Infinite. So then in that case, actually, there is no usage of clock.
Oh.
That is one of the examples I have noticed. but
yeah. I also for a simple circuit, for example, like when we make a circuit that is not fully if there's no clock involved, more asynchronous circuit is preferable, especially if, for example, if I need a low power design or something like that.
Yeah, but when it comes to low power design means I don't understand. What is the meaning of that? Low power means?
For if I can avoid, for example, power consumption for the clock.
That's right.
I usually prefer an
Yeah.
asynchronous
So yeah,
design.
that's right. But that's where it, of course, in that case, also what you prefer is that it's a simple circuit. It is not really.
Yes, yes.
I was trying to understand really an application. Yeah. Of course, as far as your circuit is very simple, then in that case, of course, you can go for asynchronous without any problem. But then then you have to find out whether we need this complex analysis.
Yeah.
Because if
For example, the weakness of the asynchronous circuit is always race and hazards, especially race, because when I apply the design, if you even if using FPGAs, it's all dependent on the quality of the components, for example, or complexity of the components. The more gates, the more the race condition or the hazards, even propagation delays occurs.
There is no doubt on that, of course. Because not only that, actually, as far as really two different types, such as really, if you have really like microprocessors or microcontroller with processor like using CMOS, is usually CMOS. And then when it comes to gates, is all the time, most of the time TTR.
Yeah.
That itself really, that itself is a troublesome.
Yeah.
That itself is troublesome. So people expect that, oh, no problem. So they know it is not the case. Actually, the delay is entirely different.
Yeah. The propagation delay is cannot be handled by the weakness is that the propagation delay sometimes cannot be handled by the for example, even if I change the type of the ICs or
Yeah.
it's always will troublesome.
But this is sometimes it's normal that really we get a race condition, but when it comes to critical race condition is, of course, then that is where the problem comes. So then identifying also the problem sometimes is difficult. That is the thing. Because the thing is that if the circuit is complex, from where really you find out, oh, you have to go through all. So then you have to sometimes isolate.
Yes. There's so much problem.
We presented. Yeah.
Okay. Any question from
students understood what I explained?
Yeah. I will explain more about for the students. Usually the asynchronous, for example, that it is the last time that we made a 4-bit counters. The clock generation of that counters is generated by our hand, for example, like that. That is one of the example of the asynchronous circuit. Yeah, there's also a synchronous circuit that can be created, but the simplest one usually involve simple flip-flop, for example, RS or JK, and we clock it for some like mode 6 or mode 8 or even 4 bits.
Yeah, but because probably the counter you would have designed is just you use the clock really only to start, no?
Yeah,
and the rest is really automatic. No.
I try to teach the students that they clock it manually. That's why
manually. Okay.
They clock it manual, so that's why we can introduce, like, for example, bouncing, propagation delay, or like that kind of case, right? If we use the
manually,
yeah. Even if we use the internal clock of the FPGAs, sometimes the students cannot handle. What kind of like example, the mechanical bouncing is can occur even if we use good materials. Now that's why part of the education, the lab is to introduce that kind of problem that they can see in
Yes,
the
that's right.
real,
I mean, they should understand that really the avoiding all these is not so really straightforward.
yeah.
They should understand that. That's the basic
Okay.
thing. Yeah, yeah. I mean, and that's where really the practical class is essential, of course.
Yes.
Without practical class is quite difficult. Yeah. Okay. Okay.
Okay.
So then I will see you again only next week. No.
I don't know. Maybe I will ask Daniel about the next schedules.
Next one is for me is I can remember that shift registers or something is the next class.
Oh, okay.
No,
No,
week after.
because the one that I remember is that next week is the students is already starting their midterm exam.
That's right. Week after next only. Not
13 December. The students said that it will be 13 of the 13 December 13th, sir.
next one.
Yeah, the next one.
Is that so?
Yeah, I don't know. Yeah, maybe about 2-3 weeks. Next month. That means.
Yes. Tuesday, 13th December.
Yeah, 13th of December.
Yes. Shift registers and counters.
Yes.
Okay. Oh, that's okay. 13th December. Yeah. Okay. Yeah, I must write down these things. Actually, I have
Yeah.
because the way really who is this Daniel sent me, it doesn't go directly to the calendar.
Yeah. It's a problem with me too.
I have to enter manually.
Yeah, sometimes the email cannot link to the calendar automatically.
That's right. Okay. We will see only 13th December and 20th December. Okay.
Okay.
Right. Thank you so much. Hope.
Thank you so much for the
Students.
teaching.
I was able to give some, but important ones, yes, I should be able to deliver. But
Yes.
some slides I had to really go, because if they should understand some fundamentals, and they're not really all, no, of course, but during a practical class, yes, definitely they will be able to understand properly. Okay, see you next time.
So okay, see you next time. Students, see you next time also. Okay, don't forget for the lab tomorrow for LA 40 and LC 40 in Thursday. Okay.
Thank you for today lecture, sir.
Okay.
Thank you for lecturing us, sir.
Thanks. No problem. You're welcome. Don't worry. Thank you, sir. So you have to understand practical.
Yeah.
Okay. So bye.
Sorry. Goodbye. Goodbye and good night.